A is area of cross section, and this rho is a constant and its value is decided by the nature of the material. So, nature of the material is taken into account by the constant rho, and this constant is called resistivity. Or specific resistance of material. So, from this equation you can see that resistance of a conductor in the shape of a wire depends upon the nature of the material used for making the conductor, area of cross section A, and length L of the material. Now, let us discuss in detail about the specific resistance of the material. From this equation you can write rho, this is equal to R A over L. Now, if A, the area of cross section of the material is 1 meter square and length of the material or the conductor is 1 meter, in that case what will be the value of rho? Rho will be equal to R into 1 meter square over 1 meter. This is equal to R ohm meters. So, units of resistivity are ohm meters and its value is equal to resistance. In which situation? In the case when area of cross section of the conductor is 1 meter square and length of the conductor is 1 meter. So, from here we can define what is resistivity. So, resistivity is the or specific resistance is defined as the resistance of one meter length of a conductor of area of cross section one meter square. So, this defines the resistivity of a conductor and it is constant for the material of a conductor. It depends upon the material of the conductor. Another way to define the resistivity is that if area of cross section is 1 meter square and length of the conductor is 1 meter, how much is volume? Volume of the conductor is area of cross section into length, and area of cross section is 1 meter square, length is 1 meter, that means area of cross section becomes 1 meter volume becomes 1 meter cube. So, this gives us another way to define the resistivity of a material, that if we take 1 meter cube of a material then the resistance between the ends of this material will be resistivity of the material. So, another way to define resistivity is that resistivity can also be defined as the resistance of one meter cube of a material. So, this is another way to define the resistivity, which is constant for a material, for a particular material. And units, as we have already discussed, the units of resistivity are ohm meter. Depending upon the value of resistance, the materials can be classified into 3 categories. So, next we will discuss classification of materials. Materials are classified as conductors, insulators, and semiconductors. So, these are 3 classifications of materials depending upon the value of resistance. For those materials which have got very low value of resistivity, they are called conductors, and those materials which have got very large value of resistivity, they are called insulators. So, the charge can flow quite easily through the conductors, and it suffers a large hindrance through insulators. The semiconductors are those materials which lie between conductors and insulators. In certain situations, certain environmental conditions, they behave like insulators. In certain other conditions, they behave like conductors. So, they are in between conductors and insulators. So, this is the classification of materials depending upon the resistance of the material. Next, we will discuss about the 4th factor which affects the resistance, and that factor is temperature. So, we will discuss variation of resistance with temperature. So, why resistance varies with temperature? When the temperature of a conductor is raised, what does it means? It means that we are increasing the kinetic energy per molecule inside the conductor. So, when kinetic energy per molecule of the conductors increases, their vibrations, vibratory motion, that becomes more vigorous. When their vibratory motion becomes more vigorous, in that case, the charge flows which flows through the conductor, or the electrons which move through the conductor because of the application of potential difference, suffer large number of collisions, and as a result of that, the resistance of the material or the hindrance offered by the material to the flow of charge increases. So, therefore, as the temperature of the material increases, the resistance of the conductor increases. This variation is different in case of insulators and semiconductors. Here we will discuss about conductors only. So, as the temperature rises, the resistance of the material increases. Suppose R naught is the resistance of a conductor when the temperature is T naught, and this temperature is changed from T naught to T and the resistance changes to RT. So, there is a change in resistance. How much is change in resistance? Let it be delta R. This is equal to RT minus R naught with a change in temperature. How much is the change in temperature? Let it be delta T, which is equal to T minus T naught. So, a delta T change in temperature results into a change in resistance of delta R. Experimentally, it is observed that this delta R is directly proportional to R naught, the original resistance of the conductor. Larger the original resistance of the conductor, more will be the change in the resistance of conductor. Again, this delta R is also proportional to delta T, the change in temperature. More the change in temperature, more will be the change in resistance. So, if we combine these two factors, then we can write this delta R, the change in resistance of the material with the change in temperature, is proportional to R naught delta T. Taking alpha as the constant of proportionality, we can write this delta R to be equal to alpha R naught delta T, where alpha is constant of proportionality called temperature coefficient of resistance. So, this alpha is called temperature coefficient of resistance. So, we will define this temperature coefficient of resistance now. Delta R is equal to alpha R naught delta T, and from this equation you can write alpha is equal to delta R over R naught delta T. So, from this equation you can define the temperature coefficient of resistance as change in resistance. Delta R is change in resistance per unit original resistance. R naught is the original resistance of the conductor before change in temperature, per unit change in temperature. Delta T is the change in temperature of the conductor. So, if delta T is equal to 1 Kelvin and R naught is 1 ohm, then alpha is equal to delta R. So, from here you can define alpha as the change in resistance per unit resistance per unit change in temperature. Units of alpha are ohms divided by ohm and units of temperature. So, ohm cancels with ohm, Kelvin minus 1 are the units of temperature coefficient of resistance, or if you measure temperature in degree centigrade, then degree centigrade minus 1 are the units of temperature coefficient of resistance. And from this equation you can find out what will be the new resistance of the conductor at changed temperature. So, delta R is R minus R naught. This is equal to alpha R naught delta T, or the new resistance R, sorry, it is RT. The new resistance RT at temperature T can be written as R naught plus alpha R naught delta T. Taking R naught as common, you can write it as R naught 1 plus alpha delta T. So, this formula gives you the new resistance of the material when there is a change in the temperature of the material. So, knowing the temperature coefficient, which is constant for a particular material, you can find out what will be the new resistance at the changed temperature of the substance. So, this is how resistance depends upon temperature of the material. Next, we will discuss about the resistances being connected in series and parallel. So, first of all, we will discuss resistances connected in series. Now, the two components are said to be connected in series if same amount of current flows through the components. So, let us consider two resistances R1 and R2 being connected in series. Let a potential difference V is applied across these two resistances. A potential drop V1 will appear across resistance R1 and V2 will appear across resistance R2, and a current I will flow through these two resistances. The current flowing through these two resistances is same. So, these two resistances are said to be in series. Apply Ohm's law, V1 is equal to I R1, V2 is equal to I R2. Now, suppose Rs is the equivalent resistance. Then for Rs we can write V is equal to I Rs, because when Rs is the equivalent resistance, the whole of this potential drop will appear across Rs. And from this diagram we know the potential difference between this end and this end is V. So, the total potential difference V is equal to V1 plus V2. Therefore, V is equal to V1 plus V2. Now, you can substitute all the three values of V1, V2 and V from these equations into this equation, and you can write IRS, this is equal to IR1 plus IR2. Cancelling I from both sides, you can write RS is equal to R1 plus R2. This gives you the equivalent resistance when two resistances R1 and R2 are connected in series. Thank you.